Hello everyone. Today I will be explaining how to connect a Colpitts oscillator using a BJT. So here we need components. Those are resistors, capacitors, a BJT, a 10 kilo ohm pot, and the devices like regulated power supply, inductance box, CRO, and other components. Now I will show you how to connect Colpitts oscillator using breadboard. So first I will be taking R1, that is 47 kilo ohm. So here this one is 47 kilo ohm. I will be taking 47 kilo ohm. So I am connecting to one point here. So one end of 47 kilo ohm is connected to 12 volts. So I am connecting this one, that is the common point, and other end is this resistor. Next I will be taking a transistor. The transistor what we have used is SL100, that is NPN transistor. So here transistor has 3 terminals. Here we can clearly see a notch is there, a small notch. The terminal near to notch is emitter. If you move in clockwise direction, the first one is emitter, followed by base, and this one is collector. So for easy things, what we have done here, the yellow color emitter, blue color base, and the red color collector. Emitter, base, collector. So base I am holding now. So base I am connecting at this point. So this one is collector. Collector I am connecting to the upper side, and this one emitter. So I repeat once again, this one base, this one collector, and the emitter. For the base, as we seen in the diagram, so this one base, collector, emitter. For base I have connected 47 kilo ohm, and the other end of 47 kilo ohm is connected to common point, to where in the later I will be connecting 12 volt VCC. Now I need to connect 8.2 kilo ohm. I will be taking a 8.2 kilo ohm resistor. So this 8.2 kilo ohm I will be connecting to, one end of 8.2 is connected to base, other end I have directly connected to ground. So if you see the diagram, one end is connected to base, another end is connected to ground. Now I will be taking the third one, RC, that is 2.2 kilo ohm. So one end of 2.2 kilo ohm is connected to collector, another end is connected to 12 volt. That is common point what I am using now. Now I am taking a 2.2 kilo ohm resistor. So one end is connected to collector terminal, other end is connected to common point, where I will be connecting VCC later. So these are the common points. So if I connect VCC here, all the points which are here will be getting the same 12 volts. So these are common points. Similarly, all these are common points. I will be using the common points in the below side as ground, upper side as VCC. So now I am taking a positive supply from regulated power supply. So positive side I have connected here. So that means all the points which we are using here will be getting 12 volts in common. Similarly, negative I will be connecting here. So all the terminals which are connected in this line will be getting ground connection. So the next one is this 560 ohm. So I have taken 560 ohm resistor. So this 560 ohm resistor, one end I am connecting to emitter, another end I am directly connecting to ground. So these are the basic connection: R1, R2, RC and RE, base, collector, emitter, plus VCC and minus VCC. Now we will come to two coupling capacitors, C1 0.47 microfarad and C2 another 0.47 microfarad. So I will be taking two capacitors, capacitor to this one. So from from emitter, so this one collector terminal, sorry again. So from collector I will be connecting this capacitor. Again from base I am connecting another capacitor. So C1 and C2 are connected. Now we need one more capacitor, that is 47 microfarad. So I will be taking this 47 microfarad. So here one end is positive, another is negative. We can clearly observe one end is lengthier, another one is shorter. The lengthier one is positive, short one is negative. So to the emitter side I have to connect positive, and the shorter one, which is negative, is connected to ground. So this is the connection. Now we will come to the tank circuit. So this is tank circuit. So here we have 3.5 millihenry, 1 nanofarad and 2 nanofarad. So for 3.5 millihenry we have used decayed inductance box. So this is decayed inductance box. Here we can vary the value of inductance in such a way that required value can be achieved. So what we need is now 3.5 millihenry. So we are changing these knobs such that we will get 3.5. This is 1 millihenry. I am wearing this one, 1, 2, 3. So this is 3 millihenry and I need 0.5 millihenry. 0.5 millihenry is nothing but 500 millihenry. So 1, 2, 3, 4, 5. So total I am getting 3.5 millihenry. So 3 millihenry, 0.5 millihenry. So total 3.5 millihenry. So it is set to 3.5 millihenry. Now I need 1 nanofarad and 2 nanofarad capacitor. So here we have capacitor. So this on the one side of capacitor they have written 102. So we can clearly see this one, this is 102. So 102 means that is 1 nanofarad capacitor. So I will be connecting this one. So 1 nanofarad capacitor. Again I need 2 nanofarads. So 2 nanofarad means, how to get 2 nanofarad means, so since we don't have 2 nanofarad capacitor, so what we are doing, we are connecting two 1 nanofarads in parallel and I will be getting 2 nanofarad. I mean to say, for example, this is 1 nanofarad. So along with this one, I will be connecting one more 1 nanofarad. So when we connect both in parallel, the output will be 2 nanofarad. So now I will show you. So this is 1 nanofarad. So in parallel with this one, I will be connecting one more 1 nanofarad. So this is 1 nanofarad and these two are 1 nanofarads. So total 2 nanofarad, 2 nanofarad and this one is 1 nanofarad. So two 1 nanofarads connected in parallel will give you 2 nanofarads. Now, so this is 1 nano, this is 2 nano. So I have to connect 3.5 millihenry now. So this is 3.5 millihenry. So one side is connected to 3.5 millihenry. That is the 1 nanofarad side, and the other end is connected to other end of the inductor, that is towards 2 nanofarad. So now we have got a closed loop. 1 nanofarad, 2 nanofarad and 3.5, they are connected in closed loop. Now from this point I have to give one connection to C2. So now I will take a connecting wire. So from this point I will be connecting to C2. So this is the point where 1 nanofarad and 3.5 millihenry are connected, and from this point I am connecting to the 0.47 microfarad, that is C2. Now 1 nanofarad and 2 nanofarad, in between we have to connect on ground. So I will be taking another connecting wire. So these are the junction where these 1 nano and 2 nano are combined. So from this one we will be connecting to ground. Now one more feedback we need to provide from C1 to the other side of the 3.5 millihenry. So this is the feedback part. I will be taking one more connecting wire. Now this is C1. I am connecting it to C1 now, and other end is connected to where 2 nanofarad and 3.5 millihenry are combined. At that point I am connecting this one. Now our connection is almost over. Now we are using CRO to check the output. I am using channel 1. So as we all know, the red one is positive and the black is negative. So the positive side I am connecting at C2. We are checking the output at point C2. So the positive I am connecting to where C2 is connected, and the negative is connected to ground. Now switch on this one. So set it to nearly 12 volts or around 12 volts. And 0.8 or 12 volts. Now we can measure, or we can clearly see the sinusoidal waves in the output side. Sinusoidal waves we are getting in the output side. If you want to get still the clear shape of the sinusoidal wave, then we need to make one small change here. That is, at instead of 560 ohm, we can connect one 10 kilo ohm pot, and we can vary the 10 kilo ohm pot such that we will get the clear sinusoidal wave. As of now, we are getting the sinusoidal wave like this. From this one, I can measure what is the frequency of this oscillator. Now how to measure? First we have to take one complete cycle. So the cycle starts from here. This is 180 degree. Again this is another 180 degree. So nearly it's covering 0.2, 0.4, 0.6, 0.8, 1.4. So 1.4 I have to multiply with time base. So in the time base it's showing at 5 microseconds. Yes. So 1.4 into 5 microseconds. So 1.4 into 5 microseconds I am getting, so 7 microseconds as time. So if I inverse it, now I will be getting around 142 kilohertz. So the frequency of this Colpitts oscillator is 142 kilohertz.